So what we're going to be doing today is we're going to be doing probability, right? Probability is, as I said, a really interesting topic. It's also a very important topic, and it is basically apply in all aspects of your life, right? Probability is how likely an event is to occur, right? Usually when we are measuring probability, we measure probability between 0 and 1, right? So if you're working out the probability of something, it'll always end up being between 0 and 1. And you can see here in this last line here, we have the probability of some event A. It could be anything, the probability of a monkey falling from the sky right now, right? And that probability will always be between 0 and 1. Now, if something has a probability of 0, that means that that event is impossible and it cannot or will never happen. If something has a probability of 1, that means that the event is absolutely certain and it will happen, right? So we could see here we have the two extremes of impossible and absolutely certain. But then we have all of the values between 0 and 1. So whether you're talking 0.25 or 0.5 or 0.78925, and we have a whole range of values between 0 and 1 here that we could say is our probability. Imagine you're a small company, right? And you want to find what is the probability, like you're a small company and you're making shampoo. And the shampoo have, you're using organic things for the shampoo. If the shampoo have, zabuka and lemongrass and all kind of madness in it, right? You want to find what's the probability of your product killing somebody. Is it impossible for your product to kill somebody, or is it certain that your product will be fatal? Right?
It's a possibility.
It's a possibility, but you want to know how probable it is. What is the probability of it? Because if that probability is close to 1, then you're sure you don't want to make that product. But if the probability is close to 0, then maybe you could take a chance and make the product. And you could probably just list some side effects and thing, But at the end of the day, it'll be really impossible for your company to go and search the entire world. It'll be impossible for your company to go and say, well, all right, we'll give everybody in the world 7 billion bottles of shampoo. We'll let all of them try it. And then, that's kind of impossible. It's hard to do. So what we will do is we will take a sample. We'll take a sample space. So out of Trinidad, we could take about 1,000 people. And that 1,000 people will be our sample space. And then we could try our experiment in this sample space here. And to see how much out of the 1,000 people dies. And if 1 out of 1,000 people dies from your shampoo, then the probability that somebody is going to die from your shampoo will be 1 in every 1,000. And, well, maybe you could decide if to release the shampoo or not, right? So we can see that probability plays a role in everything when you're talking about marketing and distribution, products, any kind of research, if you're doing PhD research, Probability is a huge thing, and we want to be able to calculate it exactly, right? So what Sasha was saying, hopefully by the end of this session, we will be able to calculate the probability of winning the lottery, right? So I have a 6-sided die, and I want to know what is the probability of getting an odd number. So a die, it does look like this. And I have the numbers on the side, 1, 2, 3, 4, this is 1, this is 1, 2, whatever. And I have a 6-sided die, so it have 1 to 6, right? When I toss this thing, what is the probability of getting an odd number, right? So at the end of the day, I have this universal set here. And this universal set is the sample space. And in the sample space, I have all of the possible outcomes. So if I have a dice, one die, right, from 1 to 6, what are all of the possible outcomes when I toss? When I toss it, what are all of the outcomes that I could possibly get?
1 to 6.
Right, 1, 2, 3, 4, 5, 6 then. So that is all of my possible outcomes. It had no way I go get 7. Yeah? So all of the possible outcomes will be in this universal set. And that is the sample space. So you understand what the sample space is?
Yeah.
All right, Sasha, you okay with the sample space?
Yeah.
Right. So inside of the sample space, I have all of my possible outcomes. But they asked me what's the probability of getting an odd number. So inside of the sample space now, I have this event, the event A. And in this event, you see I have all of my odd numbers. And then I have this event, the event B. And in this event, I have all of my even numbers. So you can see here that these are all of the possible odd outcomes. And these are all of the possible even outcomes. So an event is the set of outcomes. Yeah? And those outcomes are a subset of the universal set. So they're inside of the universal set. The universal set having all possible outcomes. But then this event here is all of those odd outcomes. And this event over here are all of the even outcomes. And I separated them. Right? So do you guys understand what an event is?
Yeah. Yes.
Nice. And then now inside of here, I actually have my data points. The actual numbers, 1, 3, and 5. These are my sample points. This is the actual outcome. When I toss the die, I will get a 3. Or I could get a 4. You know, these are the actual outcomes. So these are my sample point. So my sample point, you can see the inside of these events. And these events are inside of my sample space. So you all understand the difference between a sample space, an event, and a sample point. So, equally likely events, right? We're talking about the same six-sided die. And your microphone on, right, Sasha? So, no scene. We're talking about the same six-sided die here, right? Now, what is the probability of getting an odd number? So you could see here, you could see here that event A, this subset is the subset of odd numbers, right? So what is the probability of event A occurring? What is the probability that I will get an odd number, which is event A? Right? The probability will be equal to the number of favorable outcomes divided by the number of total possible outcomes. The total possible outcomes. So you can see here we put it in mathematical terms, right? So the number of favorable outcomes will be the number of odd numbers, right? We want to find what's the probability of getting an odd number. So how many odd numbers do we have, right? And we dividing that by the total amount of numbers, right? So let me ask you something. The probability of getting an odd number, right? So that's the probability of getting event A, right? How many was the number of odd numbers I have here?
3.
Right, I have 3 odd numbers. And what's the total amount of outcomes I have here?
6.
6. So therefore the probability of getting an odd number will be 3 over 6, which is a half. Right? So you have a 50, if you toss a die, you have a 50-50 chance, right, of getting an odd number. So everybody okay with this?
Yeah.
All right. Now this here, this formula here is super important. Write it down. This is essentially the basic formula for all probability, and every single probability thing that we do in the future will depend on this formula here, right? The number of favorable outcomes, which is the number of things you're measuring. So you want to find the probability of odd numbers. Well, how many odd numbers over the total amount of what you have, odd and even, right? So, impossible events. What is the probability of finding a person who have 3 heads, right? Let me just say, you know it's pretty much impossible to search the world to find a man or a woman who have 3 heads, yeah? Now, if we look at it here, we're looking at our sample space, right? All the possible outcomes. So the sample space will be planet Earth. And on planet Earth, how many people will we find with 3 heads? Right? This is just like Romeo's flying monkey. Right? At the end of the day, you'll see here that I have this event A. And this event A, it don't have no people with 3 heads in it. At the end of the day, I searched the whole planet and I couldn't find none. Yeah? And event B, you have 7 billion people and all of them have 1 head. Right? So you could see here that this event A is an empty set. Yeah? Is an absolutely empty set. So when I want to find the probability of event A occurring, I am finding the probability of 0 then. I find in the probability of an empty set. It have nothing in there. Yeah? So if I want to find the probability of event A occurring, event A being the people who have 3 heads. That is the number of people that we found who have 3 heads all over the total amount of people in the universal set, which is 7 billion, right? So that is 0 over 7 billion. So therefore, that probability is 0. It is impossible. And we spoke about this. Right? So therefore, this is what I want you guys to remember over here. The probability of an empty set will always be equal to 0. Right? If the set have nothing in there, then when you do your calculation, you'll end up with 0. Right? Everybody understand this example?
Yeah.
Nice. A certain event. So a certain event, what is the probability that a person will die? Right? And let's just say that that people who die on planet Earth, right? We have found an event B, immortal people. We found no immortal people. Event A is people who will die, and we found that everybody will die. It's a certainty. Yeah? So what we find is that all of the people on planet Earth will die. Yeah? All of the people. Isn't the sample space all of the people in planet Earth? The sample space, the universal set, has all of the people in planet Earth, and every single one of them is in this event over here, the event of people that will die. So therefore, when you're talking about the number of people that will die, that is equal to the number of people in the whole universal set. Yeah? So these two guys are actually equal. So therefore, if I want to find the probability of how many people will die, that is the number of people that will die over the number of people in the universal set, which we saw is the same. So therefore, these two will cancel, and you'll get a certain event to be 1. So does everybody understand this example of a certain event? An event and its complement. So just now, things gonna start to get a little bit tricky, right? So that's why I want to make sure you guys understand all of these little things. So, anybody remember what a complement is? What is a complement? A complement.
I think it's everything outside of the circle.
Right. So everything that is not in the set A. So if I have the set A here, A complement is everything that is not in the set A. So you could see here that I have a two-sided coin and it is tossed. What is the probability of A getting heads or B getting tails, right? So this is an event and its complement, right? So we could see here that I have the event A, and that event is the set that have heads in it. And then anything that is not in that will be A complement, which is the set that have tails in it. So obviously tails cannot be inside of here, because this is the set with heads. So this event here is event A, and event A is the probability of getting heads. And then A complement is the probability of getting tails. So essentially now, what we have to remember about this is, look how heads is in this set, right? And tails is in this set, right? And basically heads and tails this form our entire universal set. It forms the entire sample space. Yeah? So, it is certain, therefore. It has a probability of 1. There is a certain probability of 1 that when you toss that coin, you're going to get either heads or tails. And so whatever the probability of getting heads is, right? You add that to the probability of getting tails, and both of those will be equal to 1. Let's work it out and see, right? Can anybody tell me, or can anybody work out what is the probability of getting heads? So the probability of getting heads being event A. That is the number of things in event A, and all over the total amount of things that happen in. Yeah? So the number of things in event A, that is just heads, so that is 1. And the total amount of things that happen in, right, that is heads and tails, so that is 2. So therefore the probability of getting heads is 1 over 2. Of course it makes sense, that is one side of a two-sided coin. So the probability will be 1 over 2. Right? So essentially the probability of getting heads will be the number of heads there are, which is just 1, all over the number of total outcomes, which is heads or tails. So that's 1 over 2. Right? Where's the probability of not getting heads? That's the probability of getting tails, right? So that's the number of tails you have all over the number of universal things, which is also 1 over 2. Alright? So you understand this so far? Alright. So the point here is that if I was to add the probability of one event A plus the probability of that complement, A complement, I will always get 1. It is certain that if I toss the coin, it is certain that I will get either heads or tails. So if I add up the probability of both of them, that should be a certainty of 1, right? You understand that? So you're going to need to remember all of these things, right? Now, a way to make a note of this, and I also want you to make a note of this. Simply because we could treat this like an equation. So if I wanted to find the probability of an event happening, I could just take the certainty of 1 and minus the probability of the event not happening. And I will find the probability of the event happening. So it's just basically I take this probability and fling it across. Right? So you guys understand how I ended up with these statements? All right. Well, since all you're good, tackle this question. I'll give all you 5 minutes, right? So a bag contains 60 marbles. You have 45 green, 15 red. All right. What is the probability of getting a green marble? What would that be? Right, that's pretty much it. So you have the number of green marbles, right, divided by the total number, right? And just remember your mic on, right?
So you have to write that formula?
You should keep statements right through, right? Yeah, you should in some way. If you want to write, the number. If you want, you could write it out in actual, like the number of green marbles over total number of marbles. You could write it out like this too. So what it was, 45 over 60, which is what? Right, so 3/4. So you have a 3 in 4 chance of picking out a green marble, right? What is the probability of getting a red marble? That is the number of red marbles over the total number, which is what? Which ends up being a 1/4. So you have a 1 in 4 chance, right? What's the probability of getting a yellow marble? Well, that's the number of yellow marbles over the total number of marbles, which is what? 0 out of 60, which is 0. So it's impossible. And let's just talk about this one here, D. Where's the probability that when you dip your hand in the bag, you'll get either a green or a red? So this one here is impossible. And think about it, It's a real common sense kind of question. You have 60 marbles in the bag, right? What is the, you have 45 green and 15 red. What is the probability that when you dip your hand in the bag, you'll get either a green or a red? Where's the probability? You should be able to answer that without any working, just straight off the board. Absolutely. It's certain, isn't it? Isn't it certain that if you dip your hand, you're going to get either a green or a red because it only have green and red marbles? Yeah? Right. So does everybody understand this question here? I think you all do, right? All right, nice. You see, probability is a nice, easy thing, and it's super interesting too. Now we get into the interesting part, and now it'll get a little bit tricky. Just a little bit, though, not too much. Not algebra kind of tricky, Right, so I have this question here, and this question is a little bit tougher, right? Because we're talking about 3 fair coins. Now, the reason why they say fair is to make sure it I have no funny business. The coins are not weighted or anything, so the coins are fair, right? So 3 fair coins are tossed. Determine the sample space for all of the possible outcomes, and hence calculate the probability that the 3 heads, you'll get 3 heads on a single toss. If it is you toss all 3 of them, that you'll get 3 heads. What's the the probability of that? And what's the probability that if you throw all 3 of them, that you'll get 2 heads? Right? Any ideas as to how to tackle this? The first thing we need to do is find out what are your total outcomes. Right? So if we have here, let me just call this the first coin, the second coin, and the third coin. Right? We'll just call that the first, the second, and the third coin. You have one of the outcomes that says that you will get all 3 heads, and so that is one outcome, right? You have another outcome that says that you'll get all 3 tails, and can you list out or try to work out how many outcomes it'll have in total? Alright, so I have first coin, the second coin, the third coin, right? So in the first outcome, I hit 3 heads, right? In the second outcome, I'll hit 2 heads and a tail, right? In the third outcome, I'll hit my 2 heads and a tail again, but it'll come different this time, right? In the fourth outcome, I could get the tail first and then the 2 heads. So these 3 just handle my 2 heads and a tail. That's all of the possible outcomes. 2 heads and a tail, right? Now I can handle my 2 tails and a head, right? So if I have a head and 2 tails, then I could have the tail first, and then I could have my heads last. And now I could have all 3 tails. So how much is this? 1, 2, 3, 4, 5, 6, 7, 8. 8 outcomes in total, right? So what is the probability that you will get 3 heads on a single toss? Well, we could see here that it only have one outcome, right? So the probability of 3 heads is equal to the number of outcomes that have 3 heads. Well, that is only 1 over the total amount of outcomes, which is 8. So therefore, that is you have a 1 in 8 chance of getting 3 heads, right? Or the probability of 2 heads. Anybody want to answer that question? What's the probability of 2 heads? Nice, very good. Because you're seeing here that I have these outcomes here that have 2 heads in them, right? And I only have 3 possible outcomes where I'll get 2 heads. So I have a 3 in 8 chance that I will get 2 heads. And I mean, I don't want to I don't want to advocate gambling, but you could basically see how knowledge of probability could help you in gambling. Yeah, especially when it comes to people who does go in casinos and count cards, or you're watching the throw of the dice, or coins, or all of these random things. You could actually use probability to see if you could improve your chances of winning. So in this case now, which one would I bet on? I would definitely want to bet on this rather than this, right? Nice. So does everybody understand? I know this was a little bit of a tricky question, but what the purpose of this question was really to determine the sample space for all of the possible outcomes that we could have. So in probability, you have to do this kind of thinking, yeah? And you have to be thinking on this level, right? So let's talk about mutually exclusive events, right? So mutually exclusive events, when two events are mutually exclusive, then that means that either one or, look at this word here, or the other may occur. Either one could occur or the other could occur, but they could never occur at the same time. So this is what we call a mutually exclusive event. That is when they cannot happen at the same time. So for example, if a coin is tossed, right, you could either get heads or you could get tails. Either heads or tails. But you could never get both heads and tails on a single toss. So therefore, heads and tails, those two events are mutually exclusive. So does everybody understand what mutually exclusive means? All right. Now let's look at this here, right? We have the universal sample space here of total outcomes, and you have outcome A being heads and outcome B, event B being tails. So I have this event A, heads, right? Heads. And this event B is tails, right? And you notice something, either heads or tails could happen, but they both cannot happen at the same time. So you notice these sets do not intersect. So look at what I have here. And this is why your knowledge of sets will kind of play into it. Anybody remember what this symbol here means? Right, intersect. And you could see, you remember, intersect is when, it going like this, and you have this area here, and that is the area of intersection. But you could tell these are mutually exclusive, so they do not intersect. Remember, if they were intersecting, then this little piece here, this little intersection piece here, we could call that A and B. Yeah? So when we have an intersection, we could call that an AND. Because in the intersection, you have both A and B happening. But in a mutually exclusive event, there is no intersection. We see here A intersect B is an empty set. There is no intersection. So you can never have A and B happening. You could only have A or B happening. Right? So when we're talking about and or, these are two very, very important words. And or. Right? These words are going to define probability for us from now on. So imagine now, I have the probability of A or B occurring. When we're talking about the probability of A or B, we use a union. Yeah, you could see on this side here the probability of A and B. We use an intersection, right? But these two are not intersecting. So we have the probability of A or B. And when they are mutually exclusive, that means they can never happen at the same time. When these things are mutually exclusive, that means that the probability of A or B is written like this, the probability of A union B. This means when we're talking about statistics, in sets it means A union B. In statistics, this union sign refers to or. So if it is that I want to find, what is the probability of A or B? Well, what I would do is I would add the probability of A plus the probability of B. Yeah. So in this case, we could see here that the probability of A, since we're talking about a coin, and a coin is heads, so the probability of A will be a half, plus the probability of B will be a half. So therefore, the probability of A or B is certain 1. It's certain that you will get either a heads or a tails. Alright? Now, I want you guys to please make note of this. A union B. That is basically means A or B. For mutually exclusive events, they have no intersection at all. Right? So, does everybody understand this basic concept of the probability of A or B mutually exclusive events? Alright, very nice. So similarly now, because remember over here I have 2 mutually exclusive events. Similarly, if I had 3 mutually exclusive events, then it would be the probability of A or B or C. And all I would do is say, hey, the probability of A plus the probability of B plus the probability of C. That's all, right? Now, what we call this the addition law of probability. So the addition law of probability for mutually exclusive events. So when events are mutually exclusive, we could say that the probability of A or B or C or D or E ... going straight to infinity is equal to the probability of A plus the probability of B plus the probability of C plus the probability of D plus the probability of E plus ... Right? So does everybody understand the addition law of probability? Now I want you guys to remember something. Or usually associates with addition. Yeah? Addition, when you're talking about addition, you're talking about or. Or means addition. So just remember that. And you'll see why just now, right? So we have a question here. And let me see if you guys could do this question, right? You all want to take 5 minutes with it? So I have 25 people with broken limbs. I have 16 patients. I have, 16 pregnant patients. I have 24 patients with eye problems, and I have 35 nurses. And let me add this up myself, right? 25 plus 16 plus 24 plus 35 is indeed 100. So I have 100 people total in my sample space, right? A, the probability of getting a person with a broken leg. We could see here that the broken leg people is 25. So that'll be 25 over 100, which is 0.25, right? B, the probability that a person is pregnant when you pick them at random. Well, we have 16 patients who are pregnant there. So that'll be 16 over 100, which is 0.16, right? C, the probability that a person has an eye problem. Right? How many people have eye problems? 24. 24 over 100, which is 0.24. D, the probability that we have nurses, that we choose a nurse out of everybody, right? So how many nurses do we have? 35 nurses. So that's 35 out of the 100 people, which will be 0.35. And now we come to the greatest question of all, E. What is the probability that you are going to choose a patient? 65 out of 100. Yeah, add it up. Yeah, add it up correct this time? Now, how did you work that out? The total number of patients over the total the number of persons, right? Right. So that seems easy enough. The total number of patients is 65 over 100 people total, so 0.65. But there is another way to work it out, right? The other way to work it out, the probability of that you choose a patient, that is the probability that you choose a broken limb person or a pregnant person or a eye problem person. And so that will be the probability of a broken leg person, 0.25. And if I want, let me write out the actual thing. That means that is the probability of a broken leg person plus the probability of a pregnant person plus the probability of an eye problem person. Right? So that means that I have the probability here of a broken leg person is 0.25 plus the probability of a pregnant person is 0.16 plus the probability of an eye problem person is 0.24, and if you add that up, you will get 0.65. All right, so we could see here that, yeah, we could do it this way, right? And this is actually the easier way to do it. But sometimes the question isn't as clear-cut. And this is just to illustrate that the addition law of probability actually works the same way as if you had done it in alternate ways, right? So we spoke about mutually exclusive events, and those events are events where you could either have A happening or B happening, but you cannot have both. Now we're going to talk about independent events. Now, an independent event, an event B is independent from event A if the probability of B is not in any way influenced by what the outcome of A is. Right? So these are independent events. B is independent from A. So the probability of B occurring does not depend on A at all. So A could do what he wants and B would just remain with the same probability. Right? Now, at the end of the day, let me talk about this question here. And this is a good example. I have a coin and a die are tossed. Right? What is the probability that I will get a head and a 6? Right? Now, at the end of the day, let me call this A and let me call this B. This is the coin and this is the dice. Right? Whether A is heads or tails, that in no way will influence what B is. Yeah? B has its own probability. A has its own probability. They are both independent events, so they do not affect each other. But look at the word I use in here, and. Right? So I want to know what is the probability that I will get a head and a 6. So when we do our diagram, we will see here that, I have the probability A of getting heads. And even though they're independent, they don't affect each other. Over here, I have the intersection, and this here is the probability of they getting a heads and a 6 at the same time. Yeah. So what is the probability of getting a head and a 6 at the same time? Well, we could see here that these two guys are independent events, and even though they don't affect each other, they do intersect because we are looking for a combination of a head and a 6. So we want the and the and stands for intersection, A and B. So what is the probability of A and B occurring? Well, this is the multiplication rule now. And here we can see that is the probability of A occurring multiplied by the probability of B occurring. So the probability of A is the coin. What is the probability of getting a head when you toss the coin? That is a half, and then what's the probability of B? Because B have nothing to do with A. So what's the probability of B getting a 6 out of a dice, right? Well, that will be 1 in 6, right? So you have two independent events that have nothing to do with each other, right? But what if I want to find out what is the probability of both of them occurring at the same time? Yeah, even though they have nothing to do with each other, what is the probability of these guys occurring at the same time? So what is the probability of me getting a heads and a 6? Well, I multiply them and I'll get 1 over 12. Now, the take-home message here is the difference between and or. We saw that with or, A or B, we use the addition rule. But with and, A and B, we use the multiplication rule, right? Now, how will you know what to use in a question? Well, in a question, that is when you have to look at the words that they're using. The words that they're using, you have to pay attention to whether they use and or whether they use or. And you see how I had and underline here? But no, in a question, they're not going to underline it. They're not going to have it in italics or bold or anything. So it's just going to look like a normal question. So you have to look out for the words and or, right? So this here is and. So this here is or, sorry. And over here is and. And just remember the and have the N, which is intersect. Yeah? And the or, well, that is just union. So does everybody understand this concept? So now we're talking about the multiplication law. So the multiplication law basically says what is the probability of A and B and C and D occurring to infinity if you want. That is equal to the probability of A multiply by the probability of B multiply by the probability of C multiply by the probability of D Yeah. So when we're talking about and, we're talking about multiply. When we're talking about or, we're talking about adding. Nice? So everybody good with this? So now we spoke about mutually exclusive, we spoke about independent events, but this one is a little bit tricky, and don't worry, we're almost done. This is about as tricky as it gets, right here. We're talking about dependent events. Now, at the end of the day, you all could actually work this out one time. I don't really need to teach this. It's a common sense kind of thing. Right? It is a common sense kind of thing. Calculate the probability. So I have All right, so dependent events. An event B is dependent on the outcome of A. Yeah? So the outcome of A will affect the outcome of B. So it's kind of like a dependent event, like, what is the probability of you planning a wedding? Well, that depends on the probability of your boyfriend proposing to you, So those two are dependent events. We have here, and I'll leave you guys to calculate it in your own way, right? Because when you calculate it in your own way, then you'll understand this way a lot better. So calculate, so we have here a bucket, and we could see the bucket have 4 balls in it. It have 2 red balls, and it have 2 blue balls. Calculate the probability of pulling a red ball at random. So what's the probability of pulling a red ball? 2 out of 4, yes. Because you have 2 as the total number of red balls divided by 4, the total number of balls altogether. So the probability of pulling a red ball is 2 out of 4, which is a half, right? Now, if you pull the red ball, right? If that ball is not replaced, so you're not putting it back. You're not putting it back. Now, I want to know what is the probability of pulling a blue ball at random. 2 out of 3, right? Because you're assuming here that you had pulled a red ball. So we're crossing out this red ball here. We could see that we now have a total of 3 balls. So the probability now of, and look at this term that I'm going to put here. Look at how I'm going to write this. The probability of pulling a blue ball given that I already pulled a red one. So this slash here means given, right? So the probability of pulling a blue ball given that I already pulled a red one would be 2 blue balls out of 3 total balls, because we have 3 balls now in the bucket. Yeah. So this here is an important thing, right? It's called a conditional probability. The probability of one thing happening given that something else already happened. Right? So you guys understand this concept? Sasha, you okay? Nice. And we're pretty much done there. When we're talking about conditional probability now, right? We saw here that, watch, calculate the probability of calculating the blue ball at random, right? Now, the probability of getting a red ball and a blue ball. Well, we know and is multiply. Yeah? But we're talking about conditional probability here. So the probability of pulling the red one and pulling a blue one right after. That is the probability of pulling the red one multiplied by the probability of pulling the blue one given that you pull a red one. And so you understand this statement here? We saw here that the probability of pulling a red ball was 2 out of 4. Now the probability of pulling a blue ball given that a red ball was already pulled was 2 out of 3. Right? So therefore, what is the probability of pulling a red ball and, remember, intersection means and, then a blue ball right after? Yeah? So the probability of pulling a red ball and a blue ball is, we saw that the and means multiply, right? So you had to multiply the probability of the red ball multiplied by the probability not just of a blue ball, because remember this is being pulled after the red ball, So multiply it by the probability of pulling a blue ball given that the red ball was pulled. We have conditional probability, right? And this is what I want you to remember. This formula is quite an important formula here. That the probability of A and B, right, in terms of conditional probability for a dependent event, right? So for independent events, if the two of them independent, it would just be the probability of A multiplied by the probability of B, and you're good to go, right? But that is if they are independent. But now we're talking about if they are dependent. That means that B is dependent on what happens with A. So if they are if they are dependent events, that means that the probability of pulling A and B will be equal to the probability of A multiplied by the probability of B given A, and right? So you understand this statement is the same statement we were talking about before. So the thing is that I could actually take, because these are multiplying, so I could actually take this and fling it over. And if it's a multiply on this side, it'll become a divide on the next side. And so now I could have the probability, if I wanted to find the probability of one event given another event, right? I would just need to find the probability of A and B divided by the probability of A. Right? And we got this statement from this one. So it goes like that. So it's just a formula then. Yeah. So if you want to calculate the probability of B B given A, it would be the probability of A and B divided by the probability of A. Right? So this is called a conditional probability of B given A. So you all okay with this? So you all want to try it? It's quite a tough question, but it doesn't require anything that we do already know, right? Now you can see here that we're talking about percentage, so they didn't actually give you a number of students. So obviously, when you're talking about percentage, the total, or NU, is going to be 100. Yeah? So that is just a little hint as to how to tackle this question. And I'll give you a hint, write out all of your probabilities first. So you can write out here the probability of people who fail maths, right? Write out that. Write out the probability of people who fail physics. And then write out the probability of people who fail both maths and physics. So that is maths and physics. And you see they use the word and, right? And write that out. Right, so the probability of students failing maths, that'll be the 35% over the 100, so that's 0.35. The probability of students failing physics, that'll be the 20% over the 100, which will be 0.20, right? And the probability of them failing both maths and physics, well, they give it to us here, so we don't actually have to work it out. 15 over 100, which is 0.15. So now let's get to the question. And we wrote out all of our probabilities there. Now, if he failed physics, what is the probability that he also failed math? And that is if we select a student at random. If he failed physics, what is the probability that he also failed math? Anybody? We're talking about the probability that he fails math given that he already failed physics. The probability of one thing given another is equal to the probability of him failing both math and physics divided by the probability of physics, the one that is already given, right? So he failed physics, that is given. What is the probability that he also failed math? So when you choose a student, if he failed physics, what is the probability that he also failed math? So that is the probability of math and physics divided by the probability of physics. So that'll be 0.15 divided by the probability of physics, which is 0.20, which is the same as 15 over 20, which works out to be. So if he failed math, so what is the probability now that if he failed math, so we are given that he failed math, what is the probability that he also failed physics? So now I want the probability that he failed physics given that he failed math. That'll be the probability. Yeah, tell me. So you only have physics and maths inside of this bracket here. So obviously on top you're going to have maths and physics. And then underneath the denominator is whatever is given. So the given one is the one that comes after. So it's given that he already failed maths. So that means that this probability will be 0.15 all over the probability that he failed math. We see there is 0.35. This is the same as 15 over 35. And that is 3 over 7. So we do have this last one here before we go. And this last one is a challenge. And let me see if anybody could figure out what is the probability that he failed math or physics. Now, you remember they use the word or here. Because imagine I have my universal set here. Right? These are all of the failures we're talking about, right? We have the students who fail maths. We have the students who fail physics. But then over here, we have the students who failed math and physics. And so this is a big and, this intersection here. What I wanted to know is, I want to know where's the probability that he failed math or physics. So when I pull a student out of this bucket, I want to know where's the probability of him failing math alone, or where's the probability of him failing physics alone. So the probability of him failing math or physics is just like what you said. We have the probability of him failing math. We have the probability of him failing physics. But if I find the probability of him failing math, that is this whole circle here. And if I find the probability of him failing physics, that is this whole circle over here. The problem is I do not want the and part. I don't want this. I just want the unshaded parts. I don't want the shaded parts. So what I have to do is I have to minus the probability of him failing math and physics. I have to minus that intersection. Yeah? Because the probability of him failing math or physics means that the probability of him failing math, we know that from the formula, plus the probability of him failing physics. The problem is that these two things intersect. Right? I want the or. I don't want the and. Right? So I just want this clear space, and I don't want the colored section in between. So what I'll do is I'll find this full probability plus this full probability, but then I will minus this shaded region in the middle. Right? So that means that I now have the 0.35 plus the 0.20, and from that I am going to minus the 0.15. So you see how it could get a little bit tricky, and you have to think deeply about it. Yeah, so 0.35 plus 0.20 minus 0.15, that gives us a probability of 0.4. That when we choose somebody, the probability is almost a half that that person would have failed math or physics, but not both. Not both. They didn't ask us for both. Nice. So this here, as I say, this is the last question. This is pretty much the end of all of statistics, right? And yeah, how are you guys feeling about this question? Yeah, that was it for Statistics 5. I hope you all enjoyed it. Have a good evening.